This is the first episode in Chapter 7 of Computational Optical Imaging, which deals with the coherence model of optical fields. This is our third field model after geometrical models in Chapter 4 and the wave model we've talked about in Chapters 5 and 6. So now we want to talk about why we need another field model. And to understand that, we need to understand how the optical field is detected. What we're looking at here is the full well capacity of photodetectors in a focal plane array as a function of photodetector size. This is a graphic created by Teledyne Solutions. You see if we have about a 5 micron pixel, we might have a well capacity of 10,000 photoelectrons. Going up to a 10 micron pixel, maybe we'd have a well capacity of 100,000 photoelectrons, which is, a lot of photoelectrons, but definitely in the range where quantum effects and Poisson noise are going to be important features of our measurement. But more generally, we want to think about, could we reconstruct the electromagnetic field from these measurements? What we've just talked about in episode 40 is how to make a wavefront camera, how to make a camera that can reconstruct the actual electromagnetic field incident on an aperture. And what we're going to find is that in most cases, that is actually an impossible task for natural fields. As an example, the archetypical natural field is sunlight. Here we have a picture drawn by Dolly showing the sun illuminating the Earth. The sun illuminates the Earth with a solar constant about 1.4 kilowatts per square meter. That's where that 1361 comes up in Dolly's image here. So we have 1.4 kilowatts per square meter. That works out to be about 10 billion electron volts per square micron of illumination. Which is a big number, but still a relatively small number, speaking of number of photons per detector element, especially after we account for losses in the optical system and due to reflection and so on. So if we think about the number of modes we would need to reconstruct if we wanted to model the actual electric field coming from the sun, we can think of each photodetection point corresponding to a single spatial mode, but then we'd want to think about how many temporal modes would we need to represent this flux. And so we could represent the electromagnetic field, the coherent electromagnetic field, as a superposition of temporal modes that describe the field incident on each photoelectron site. Now we'd want to describe that in terms of quantum mechanical states of the field. So the field would have a quantum mechanical amplitude with the quantum mechanical state generated by the creation and annihilation operators as shown here, and we'd have basically a photon density or number of photons in each one of the modes. Now the number of modes we would need to represent this is proportional to the time bandwidth product of the field. So we'd have to think about what's the spectrum of our illumination on our photodetectors and how long are we going to measure that for. The solar spectrum looks like this. So this is a thermal source, and so we see this extended spectrum going from the visible into the far infrared, and the density of the solar illumination in space is shown, and then we have windows in the atmosphere where solar light is absorbed. But with a imaging camera, we're mostly going to only be sensitive to light within the visible band. We'll put filters on to block the infrared to keep the image from being unnecessarily blurred. So we'll take only this 42% of the visible light that's in the visible band and consider that as light we want to measure on our photodetector. Now, the bandwidth of that works out to be around 400 terahertz, as shown here, assuming we go from a minimum wavelength of around 400 nanometers up to around 800 nanometers covering the visible band. So we have 400 terahertz of bandwidth, and now to get enough photons to fill our well, to get those 10,000 or 100,000 photons we need to fill the well, we're going to need to integrate for, let's say, 30 milliseconds would be a typical exposure time. Now, in that time, the time bandwidth product of the field is 10 to the 13th. Okay, so that's the number of modes we would need to be able to measure the light that's incident on, or to characterize the light if we wanted to characterize the actual electromagnetic field that we're measuring when imaging a thermal source. So this is the reason that we need a new field model, is that the number of modes we would need to describe the field is this 10 to the 13th, but the number of photons we're going to detect is less than a million, like 10,000 or 100,000. So we have way less than 1/millionth of a photon per mode. So if we go back to our quantum mechanical description, the noise we would have in each mode in estimating the actual electromagnetic field is way greater. We would have way less than 1 photon per mode. Our noise is going to be at least 1 photon when we make a measurement. So it's just impossible for us to describe the amplitude of the actual modes of the field. But we can describe the state of statistical averages over the modes. Now, we're going to avoid discussion of the actual quantum mechanical field theory in this course. We can use coherence models of the field to describe actual measurable quantities and describe fields without getting into the quantum mechanics, but to do that we need to introduce the new field model that we introduce in this episode. Computational imaging. Episode 41, Coherence Fields. Most of this episode is just a definition of the various distributions we use to describe the coherent state of optical fields. And here's a list of the most common functions: the mutual coherence, the interference of the field drawn from two different points in space and time; the cross-spectral density, which is the spectral analog of the temporal mutual coherence; and then the traces of those two functions, which are the spectral density and the irradiance, and the mutual intensity, which is the value of the mutual coherence for zero time delay. Now, the challenge that we face here is that detectors measure the irradiance. Detectors measure the power in the electromagnetic field, which means that they take the time average of the field at a particular point or averaged over time, and extract the average value of the Poynting vector, which would be the energy in the field, and that would be proportional to the number of photoelectrons generated by the field. So this measurement is the mutual coherence evaluated at a single point for zero time delay. This is the thing that we measure always with photodetectors, but the problem with measuring the irradiance is it's not a quantity that allows us to calculate the irradiance at other points in space, so it doesn't propagate. Many different distributions of objects can generate the same irradiance measurement. So we introduce the mutual coherence as a quantity that can be measured and that can be used to calculate the state of the field at other points in space. So here the mutual coherence is defined as the ensemble average of the product of the field drawn from point R1, T1 with the field point drawn from point R2, T2. Nominally, this is not really a measurable quantity, but what we can do is create optical systems where we take the field from those two different points and add them together. So we create a set of optics, maybe some fiber that's going to sample the field at two different points and get some time delay, add those two fields together, and then as we saw with lithography, we can see the interference between those two terms. And so we see the self-irradiance of each of the terms, the gamma 1,1, the gamma 2,2, that would be the energy in each of the field components individually, and then we'd add to that the cross terms. And so this is a measurable irradiance quantity, is the interference from this field drawn from two different field points. Now, those brackets we've said mean like an ensemble average, but we don't really have the ability to repeat the experiment over and over again to get that statistical average. What we do when we take an actual measurement is we average the product of the field from these two different points as a function of time. So that's what it means to make an irradiance measurement. We will assume that the time average of the product of the fields is the same as the ensemble average. This is called the ergodic assumption. And so we've assumed that different draws for the field from different times is the same as different statistical draws of the field. This is a good approximation for thermal sources where we're integrating for a long time compared to the optical period, which is just a few femtoseconds or picoseconds. So we're saying that we can treat this as a random process with the statistical distribution sampled by integrating as a function of time. We will also assume generally that the field is stationary, which means that the origin of the time axis doesn't matter, and it's only the difference in the two times that we're measuring the field that's a significant feature. This is not true on long time scales, like the multiple hours or seconds where we're going to turn lights on or off. It matters where the temporal origin is. But on the scale of the optical period of just a few femtoseconds, it doesn't really matter where we set the time axis when we average for milliseconds compared to something that's oscillating at hundreds of terahertz. So we'll assume, generally speaking, on this kind of integration time scale that we're going to measure the field, that only the difference in the two times, T1 and T2, matters, and that's the stationary approximation. Okay, as we saw in chapters 5 and 6, it's usually more convenient for us to analyze optical systems for fields that are narrowband with respect to wavelength, that are quasi-monochromatic, operating at a single wavelength. When we talk about coherence functions, we do that using what's called the cross-spectral density. Formally, we might want to think of the cross-spectral density as the field interference drawn from two different points, R1 and R2, as a function of frequency. The problem is that the Fourier transform of the field with respect to time is not really well defined when we've assumed that the field is stationary and the time axis can shift arbitrarily. But we can formally think of this expectation value and then replace each one of the fields as a function of frequency by their inverse Fourier transforms, which would be the fields as a function of time, as shown here. We have the field at R1, T1, R2, T2 with the Fourier transform kernels. The kernels are not statistical quantities, so they don't go inside the expectation value. This expectation value is the mutual coherence of the field at R1, R2, with the time difference T1 minus T2 because we've assumed the field is stationary. And then we can take this integral over the T1, T2 plane and separate it into an integral over tau, which would be T1 minus T2, and T, which would be T1 plus T2. The integral over T doesn't really depend on the statistical quantity gamma, so that integral we can integrate out, and we get that nu prime has to be equal to nu. We get a delta function on nu minus nu prime times the Fourier transform with respect to tau of the mutual coherence function. Now we can define a quantity which we'll call the cross-spectral density, which would be the limit as delta nu goes to 0 of this expectation value of the field drawn from two different points in space at two different frequencies. And so what we've derived as a part of defining the cross-spectral density is what's called the Wiener-Caccini theorem, that the cross-spectral density of the field is the Fourier transform with respect to tau for the stationary field of the mutual coherence function. In most cases where we're talking about the coherence function, we describe propagation of fields and the fields distributed over space, the same as we worked with the quasi-monochromatic or single frequency field in describing coherent electromagnetic fields. We'll describe the field in terms of this cross-spectral density function. The spectral density of the field, which we'd normally call the spectrum when we measure with an optical spectrometer, is the cross-spectral density evaluated at R1 equal to R2. So the cross-spectral density evaluated at a single point in space. From the Wiener-Caccini theorem, we can say that the spectral density is the Fourier transform of the mutual coherence for that single point in space. Take the Fourier transform taken with respect to the time delay, and this is the basis, of course, of Fourier transform spectrometers. And similarly, we can say that the mutual coherence function is going to be the Fourier transform with respect to frequency of the spectrum of the field. Okay, and now what we're going to measure in the end is going to be the irradiance. We're going to measure the time average of the electromagnetic field at a single point in space, but equivalently the irradiance can be thought of as the measurement of the power spectral density averaged over all frequencies. We'll often also talk about systems in terms of the mutual intensity, which is the mutual coherence function with zero time delay, where we have this quasi-monochromatic field. Oftentimes we can ignore the temporal component of the field and just talk about the interference of the field as a function of space. Okay, so those are our coherence functions. We're going to use them to analyze optical fields. Now we're going to talk about field distributions in terms of these coherence functions instead of in terms of the electromagnetic field, because as we talked about at the beginning of this episode, the electromagnetic field itself is fundamentally unmeasurable for these thermal sources of radiation. But now that we've defined these coherence functions, we can analyze how optical systems manipulate and process fields the same as we did with coherent systems in chapters 4 and 5, or 5 and 6, excuse me. So next time we're going to talk about how coherence functions propagate.